Okay, so now what we are going to do is we are going to quickly see, just make sure what happens when you look at the Taylor series in the higher dimension. We argued that when you had just one dimension, the Taylor series kind of told us why minus f dash of x is the right thing to do as a choice for the direction. Now what we are going to see is what is the analog of Taylor series in the analogous Taylor series for higher dimensions, and we will see why that is also a useful thing to look at, right. So, what was Taylor series earlier, right? So it was f of x was simply, well, rather you wanted to evaluate f at a different point, f of x plus some eta d, and we said that it can be got by evaluating the function at x plus eta d f dash of x plus eta squared d squared f double dash of x by 2 and so on. Now the higher order analog, higher order Taylor series looks like the following. Well, again you are going to evaluate the function at x plus eta d. Now the x plus eta d is actually a vector, right? Here it was a scalar because it was a one dimensional function. Now it is a higher dimensional function, but nothing much changes. So this is still going to be f of x. Again, x is a vector, remember. I mean, just want to make sure the objects are clear, though we are using the same notation. Plus, now this, you cannot simply multiply vectors like this. Now what happens in the higher order analog is that, well, the eta stays. Now d is a vector, f dash is a vector. Now what we do is we look at d transpose del f of x. Well, we know that the generalization of f dash of x is del f of x. Now d is a vector. Now we take the the directional derivative along d, which is d transpose del f of x, right. So this d transpose del f of x is a scalar, right. Again, f of x is a scalar, x is a vector. You are asking what is the function's value at a particular vector, that is a scalar. Eta is a scalar, d transpose del f of x is a scalar, and of course there are these higher order terms. Let us ignore the higher order terms for now. So there are these other higher order terms. Now this is the Taylor series expansion for a function with multiple variables. Now what do we gain by looking at this? Well, we gain the following. So now we will again ask the question, what is a good d to choose, right? So the argument is exactly the same, but then let me go through it quickly so that we understand an important point will come out of it, right? So we are again asking, so if f of x plus eta d minus f of x is, this is what we care about. We know that by Taylor series approximation, this is something like eta times d transpose del f of x. Of course, I am sure all of you already know what is d a transpose b, right. So if you have two vectors, a which is a1 till ad and b which is b1 till bd, now a transpose b will be something like a1 b1 plus a2 b2 dot 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 plus ad bd, right. So just to make sure we are on the same page. Okay, so which means that I am multiplying the corresponding component of d with del f of x and then adding them up. Okay, so now again we want to choose a d such that this value is negative, the left hand side is negative, right. So want d such that left hand side is negative. Equivalently, we want d such that eta is a positive scalar, we do not care about that. We will just say we want d such that d transpose del f of x is less than 0. Now this would be the corresponding corresponding equation that we want our direction to satisfy at any given x. Now of course, now note that if d equals minus del f of x, which is what my gradient descent does, then this becomes minus del f of x transpose del f of x, which is what we will call as minus norm del f of x squared. Well, the norm, remember the norm of any vector with itself, norm squared is A transpose A, which is A1 times A1 plus dot 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 plus AD times AD, which is sum over I is 1 to D I squared, and this is always a positive quantity, right. So, this is positive, and then I have a negative term here. So, I know that this is always less than 0. So, if I choose D equals minus del of x, then I am guaranteed that if I take a small enough step in the direction of D, then my function will decrease. It is the same analogous thing that we already saw. But the interesting thing is that, well, if you look at it, all we are saying is that as long as you have a D such that D transpose del f of x is less than 0, you are good, right. So, of course, if D equals minus del f of x, the negative of the gradient, then that is a good direction to move because your function is going to decrease, but that is not the only direction, right. So, now there can be other D's such that D transpose del f of x is less than 0, in which if you move, you will still reduce your function. Now, where are these directions, right? So, this is what we are going to ask next. Maybe I will write this here and right. So, where are the D's such that D transpose del of x is less than 0? Well, the way to think of this is as follows. Let us say I am at some point, let us say we are in 2 dimension, and there is a vector w that points in this direction, let us say some arbitrary w for now, which is w1, w2, think of this as 1 comma 1 if you will. Now, I am asking the question, where are the D's such that D transpose w equals 0, and we will see why this is useful. So, where are the D's? Of course, D is a 2-dimensional vector. Which are the 2-dimensional vectors which will make a 0 when you do a what is called as a dot product, right. So, this is called as a dot product. I am sure again you must have seen this earlier in the course. So, where are the D's such that D transpose W equals 0? Well, these will exactly be those points on this red line, right. So, which are in 2 dimension, which are what are called as perpendicular to the W vector, right. So, any point on this line, you take any point on this line, it satisfies D transpose W equals 0. Now, the question then is, where are those guys for whom, where are those D's for which D transpose W equals, where D transpose W is greater than 0? Well, this line is D transpose W equals to 0. Now, the D's where D transpose W will be greater than 0 will precisely be the guys on this side, right. So, the ones shaded in yellow. So, these are D transpose W is greater than 0. Basically, it will make a positive dot product with W, and the guys which for whom we will have D transpose W less than 0 are on the other side, right. So, this is D transpose W is less than 0, right. So, which means given a W, it kind of partitions the entire 2-dimensional space into 2 parts. In one part, you have D transpose W is greater than 0, and in the other part, you have D transpose W is less than 0. The set of D such that D transpose W is less than 0 is the green set, and the analogous one for the greater than 0 is the yellow set. What does this imply for our problem? Well, for our problem, we are at some point, let us say x, and now we are looking at, well, where is the gradient of the function pointing at this point? Let us say the gradient is pointing in this direction, del f of x, and we are looking at the gradient, and then we want to decide which direction should I move so that the function's value actually decreases if I take a small step along that direction. That is the question we are asking. Now, what is this telling us? This picture that we just saw tells us that, well, the direction that you need to move so that your function value actually decreases is on this side, right. So, you can move anywhere along the green direction. Maybe this is a possible direction, maybe this is a possible direction, this is a possible direction. There are infinite directions here. If you take a small step in any of these directions, your function value is guaranteed to reduce, right, for a small enough step size. Now, the point is the gradient descent algorithm picks a special direction which is exactly opposite to del f of x, right. So, which is minus del f of x. This is the gradient descent direction, but then that does not mean that is the only direction where you will descend. You can potentially move in a different direction and also reduce your function. You can potentially descend in any of these directions. Now, then the question comes, why should I care about the negative gradient direction? I could potentially, there may be a different direction which might be better, right. So, that is the immediate question, because now you have infinite directions to move in, and which one should I pick? Well, it turns out that, and maybe I will write it on a different page as a separate note, right, minus del f of x, there is no dot here, gives the steepest descent. Right. So, if you are allowed to move only a particular unit length, let us say, right. So, you are at this point and your gradient is pointing in this direction, and if you are allowed to move only one unit in whichever direction you want to move, and you have several directions to move, right. So, you can move one unit in whichever direction. Of course, there is no point in moving in any direction which does not make a negative dot product with the gradient, because that is not going to be a descent direction. But then if we are allowed to move in any of these directions, the one that will give you the maximum decrease in the function can be shown to be the negative gradient direction, right. So, this is minus del f of x, and this is the direction of steepest descent. So, this gradient descent algorithm is also called sometimes the steepest descent algorithm, also called the steepest descent, right. So, the gradient itself is going to point to the direction in which the function is increasing as much as possible, the maximum, the direction where the function is increasing the maximum, and so the negative of the gradient is the direction in which the function is decreasing the maximum. And so, this function is called this algorithm is also sometimes called the steepest descent algorithm. Well, that does not give us any new insights per se, right. So, other than saying that, well, we initially started off with this negative gradient, now what are we saying? We are saying that, well, that is the best thing to do in some sense, because you will get the most descent in your function if you move along the negative of the gradient. So, are there any situations where moving in a different direction other than the negative of the gradient would even make sense? Well, the answer is yes and no. The answer is really no when you have an unconstrained optimization problem like the one we are solving now, right. So, you want to just minimize f of x, right. So, that is the problem we have been looking at least so far, where you want to, if you have a x, maybe the x is in some d dimension, there is no constraint on x, and if you want to minimize f of x, then gradient descent is the right thing to do, right. So, the negative of the gradient is the right direction to move. But if you have constraints, right. So, if you now have, let us say, a constraint, and let us for simplicity look at the case where you have only one constraint and this is an inequality constraint. We will talk about the other cases in a bit, but let us say now we have this problem. Okay. So, now you want to minimize f of x, the same function you want to minimize, but then your x cannot be any possible x, it is constrained by the fact that g of x is less than or equal to 0. Remember, we had this the rope constraint which was constraining where the cow could move, right. So, it was in that case, if you remember, g of x was something like x1 squared plus x2 squared was minus some I think it was 10 is less than or equal to 0, where 10 was the radius of the rope, right. So, this was a constraint, right. So, not all x's are allowed, we are only allowed to use x from certain range. In this case, that is indicated by the fact that g of x is less than or equal to 0. Now it becomes a very interesting problem, because now if you move in the negative gradient direction, it could so happen that you will end up in a point for which g of x less than or equal to 0 is no longer satisfied. Then how do we solve this problem, right? So, we do want to solve a problem such that g of x is less than or equal to 0 is satisfied, but then we still want to minimize f of x. So, now what can we do, right? So, now in that particular case, do other directions help us somehow, right? So, instead of moving in the gradient direction, is there a different direction, or what is the deal, right? So, how can we be sure that we are moving in the right direction or not, right? So, now this is a constraint optimization problem, which is what we initially wanted to solve. Right now we have solved the unconstrained version of it. The moment you introduce constraints, you already see that there are going to be issues with the gradient descent algorithm, and we will start talking about constraint optimization problems, specifically with a single inequality constraint going forward. Maybe I will stop here for the moment.